Yeah, so we'll move on to the next talk. That is by I think it's by Dennis Pinto. Just give me a second. It's a programmable accelerator for streaming automatic speech recognition on edge devices. Dennis Pinto is a researcher at the University Politecnica di Catalonia, and I'll be playing the video right now. Yep, please tell me if you have trouble hearing the video.
Hello everyone and welcome. I'm Dennis Pinto. In this session I will present our paper, a programmable accelerator for streaming automatic speech recognition on edge devices. Automatic speech recognition, or ASR for short, is quickly becoming a mainstream technology, as we can see in these common examples of applications. These include smart speakers and AI assistants, dictation engines, devices for real-time language translation, and speech-powered wearable devices. One of the main reasons for this recent explosion in speech-powered applications is that ASR systems have become very accurate over the last few years. This figure shows different ASR systems proposed from 2016 to mid-2021. On the vertical axis, we have word error rate on the LibreSpeech benchmark. Word error rate is the percentage of word errors in the transcription, so here lower is better. As a reference, we can see here the human word error rate benchmark, as presented in a 2016 paper. The authors of that paper measured human performance by hiring professional transcribers to unknowingly transcribe the benchmark. So, first of all, let's start with a brief background on speech recognition. Automatic speech recognition is the process of decoding an audio signal to obtain a transcription. It is generally performed in a streaming fashion. Instead of capturing the entire signal and decoding it at once, we capture chunks of the signal and then perform a decoding step to obtain a partial transcription, which can be printed back to the screen of the device to provide the user with real-time feedback. So here, each decoding step is composed of three major components: feature extraction, acoustic scoring, and hypothesis expansion. The feature extraction component receives the raw signal and breaks it down into frames of a few milliseconds. Then each audio frame is transformed into a feature frame. Then we have the acoustic scoring component, or as it is often called, acoustic model. This model is generally a neural network. This neural network receives the feature frames and computes score vectors. In this example, each score is related to a letter of the Latin alphabet. The score of each letter is the likelihood that the frame contains that specific letter. The next step is to execute the hypothesis expansion component. This component generates hypotheses by traversing a decoding graph that contains all the possible combination of acoustic units, in this case letters, to form words and sentences. At the beginning of each hypothesis expansion step, we have a set of partial hypotheses, each of which is linked with a node in the graph. These nodes are called active nodes. During a hypothesis expansion step, each hypothesis is expanded by traversing every output link from its node in the graph. We obtain new hypotheses by concatenating each of the alternative letters that we traverse to the starting hypothesis. So we keep capturing chunks of the signal and performing decoding steps until the end of the utterance. So, as we have seen, these modern ASR systems are so accurate mainly because they rely heavily on machine learning algorithms. These algorithms, of course, are very expensive in terms of computations and energy consumption. The challenge comes when we try to execute these expensive speech recognition systems in low-power devices, such as mobile phones and wearables, mainly because these devices provide comparatively low performance and are often powered by a battery, so they are also limited in regards to energy. Consequently, the major approach to ASR is to capture the audio with a low-power device and send it over to a server. The server then decodes the utterance and sends the transcription back to the device. The main issue here is that sending sensitive data, such as personal recordings, to a company-owned server comes with severe security and privacy issues. So we want to process locally this type of sensitive data, and for that, we think that hardware acceleration is key. Over the last few years, there have been many proposals to accelerate machine learning algorithms in general, and some proposals to accelerate the speech recognition system. For example, in Price et al., the authors developed several chips for speech recognition. But even though their chips provide some flexibility in the design of the DNN, the chip can only execute a specific type of ASR system. There are also many DNN accelerators and even some beam search accelerators that perform the hypothesis expansion component. As a matter of fact, in one of our works, we designed an heterogeneous system that contains one of each accelerator, and then we tested its performance executing a modern ASR system. And even though the performance was quite good, however, the architecture was also limited to the execution of a rather small subset of ASR systems. We think that the issue with most of those proposals is the lack of programmability. Non-programmable accelerators are limited to a very restricted set of ASR systems and risk becoming obsolete by innovations in speech recognition technology. The proposal of this paper is called ASR-PU. ASR-PU is a programmable hardware unit to perform ASR locally on low-power devices. To determine its performance, we implement a state-of-the-art ASR system for this unit and estimate its performance in a low-power configuration. Then we estimate chip area, peak power, and average power. So let's start with the programming model of our accelerator. In this accelerator, a decoding step consists of two phases, the acoustic scoring phase and the hypothesis expansion phase. The acoustic scoring phase is intended for performing feature extraction and acoustic scoring. This phase is implemented as a sequence of kernels written by the programmer. Each kernel is written with parallel code to leverage the abundant parallelism present in these algorithms. As we will see in a few minutes, kernels are executed one after the other in a sequential manner. But during the execution of a kernel, the accelerator executes several instances of the kernel in parallel as independent threads. After this phase, the accelerator enters the hypothesis expansion phase. It consists of the execution of a single kernel implemented by the programmer as well. The accelerator will launch an instance of this kernel for each active hypothesis. Again, each instance is executed as an independent thread, and the threads are executed in parallel in the hardware. Depending on the implementation of the ASR system, each acoustic scoring phase may generate more than one vector of acoustic scores. To consume them all, the hypothesis expansion phase can be repeated as many times as necessary. For example, if we have 3 vectors of scores at the beginning of the hypothesis expansion phase, this phase will then get executed 3 times, one for each input vector. In addition to these kernels, the programmer can include a set of functions alongside each kernel. Before the execution of a kernel, the accelerator will check if the programmer provided a setup function. If that is the case, it will first launch a thread to execute the setup function. After it finishes, it will start the execution of the kernel. These setup functions can serve many purposes. For example, they can be used for prefetching model data, such as DNN weights, and also for configuring kernel parameters, which let us write reusable code, and for checking the number of available inputs before the execution of the kernel, which provides some runtime flexibility. This diagram shows a high-level description of the architecture of the ASRPU accelerator. The accelerator contains a decoding unit that serves as the interface of the accelerator with the rest of the system. The set of commands includes operations to start and stop decoding steps and to configure the parameters of the decoding steps. These parameters are stored in the configuration memory and can be accessed from the rest of the units. The main part of the accelerator is the execution unit, composed of the ASR controller and a pool of programmable cores or processing elements. The ASR controller dispatches the threads of the different set of functions and kernels into the cores and captures signals from the cores. For example, to interrupt the decoding step. The ASR controller has access to the configuration memory, where the information about the kernels, such as their location on external memory, is stored. This accelerator also contains a hypothesis unit to store the partial hypothesis in between decoding steps. This unit also contains functionality to sort and prune the hypothesis. The kernel that implements hypothesis expansion can access this unit to fetch previous hypotheses and to store the new ones. The unit obtains the necessary parameters, such as the beam width, from the configuration memory. Regarding internal memory, the accelerator contains two memory modules. The first one is called shared memory. It can be accessed from the kernel code, and it is intended for storing intermediate results, such as the outputs from the hidden layers of the neural network. The other is the model memory / dcache. This memory has two functions. During the acoustic scoring phase, it is used for prefetching and storing model data, such as DNN weights. During hypothesis expansion, it behaves as a hardware-managed data cache. This dual mechanism let us use the memory in the most convenient way to exploit the characteristics of the memory access of each algorithm. During acoustic scoring, we access model data in a predetermined way, so prefetching is the best strategy. During hypothesis expansion, the access pattern is essentially random, so prefetching is not a good option if the entire graph doesn't fit in the internal memory, which is generally the case. However, hardware-managed dcache let us exploit locality in the access of the graph. So let's now look at how the kernels are executed in the core pool. In the diagram, this rectangle represents the core pool, which in this example contains 8 cores, represented by the squares. The blue squares represent that a kernel thread is being executed in the core, whereas a yellow square represents that a setup thread is executed in the core. As previously mentioned, before the execution of each kernel, the accelerator checks whether the programmer provided a setup function or not. If the setup function is present, the accelerator will launch a thread to execute it. We start the decoding step in the acoustic scoring phase by executing its first kernel. So first, the ASR controller dispatches a thread to execute the setup function of this first kernel. This kernel will usually perform feature extraction, as we saw earlier, but that is not known by the accelerator, which treats all the kernels in the same way. This setup thread will generally load the signal data, as well as any model data, from external memory into the model memory. To do so, the setup code has access to the DMA unit associated with the model memory. Once the execution of the setup thread finishes, the ASR controller starts the execution of the first kernel by launching the required number of threads. At the start of a kernel execution, the controller reserves a core to execute the setup function of the following kernel. Executing the setup function so early is what allows us to effectively prefetch the model data. Of course, when the setup function finishes, a kernel thread gets assigned to it. Also, at this point, the setup function can check how many outputs will be computed by kernel I, the current kernel. With that, it can first determine whether the number of available inputs will be enough or not to execute kernel 1i plus 1, the next kernel. And second, compute the number of outputs that I plus 1 will generate and reserve the space in the shared memory to store them. At this point, if the setup function determines that the kernel I will not generate enough outputs to compute kernel I plus 1, it can notify the ASR controller. The ASR controller will stop the execution of the decoding step once the execution of the current kernels finishes. In the usual case, kernel I will generate enough outputs to compute the next kernel. After the computation of all the threads have finished and the DMA operation has finished too, the ASR controller starts executing the next kernel. If all the kernels can be executed, the hypothesis expansion setup function will be executed alongside the last acoustic scoring kernel. The main purpose of the setup function of the hypothesis expansion kernel is to determine how many score vectors are available, and thus how many hypothesis expansions are required. To test this design, we implemented in pseudocode a state-of-the-art ASR system, the TDS system, and estimated its performance on the ASR unit. The TDS system computes a feature frame for each 25 milliseconds of audio. The DNN acoustic model is a TDS network with 29 fully connected layers and 18 convolutional layers. The decoding graph is a lexicon tree that contains about 200,000 words. In this case, the acoustic units are not letters. Instead, this system uses word pieces, which are fragments of words obtained offline by an iterative optimization process. Every time the algorithm reaches a node in the graph that completes a word, it checks a language model to obtain a language model score. This language model is implemented as an additional graph. So, in the following slides, we can see the code snippets for some of the kernels. The first one is the process that runs in CPU. It first configures the accelerator and then enters the main loop, which fetches audio values from the microphone and sends commands to the accelerator to start decoding steps. This code implements the feature extraction kernel, which is the first kernel executed during the acoustic scoring phase. It implements the transformation of a single input frame into a feature vector and is executed once per frame. The first part of the code configures some parameters of the thread, as you will do when programming for a GPGPU. The second part of the code implements the MFCC algorithm. This kernel implements a generic fully connected layer. We rely on the setup function to configure the parameters of the layer before its execution, which allow us to use the same code for all the fully connected layers. The main part of the code is this loop here, which computes a single output for a single neuron. We will launch as many threads as neurons there are in the layer, multiplied by the number of outputs generated from the batch. In order to obtain real-time decoding with this system, we have to perform at least 13 decoding steps per second. So we tested different configurations of the units and finally decided on a configuration that provides 0.5 real-time factor performance. In other words, twice the minimum performance for real time, that is 26 decoding steps per second. This configuration contains 8 cores in the core pool. The vector units of the cores have size 4. To set the capacity of the memories, we looked at the memory requirements of each kernel. The shared memory was set to 512 kilobytes to meet runtime requirements, and the model memory was set to 1 megabyte. In this case, we don't need a memory big enough to store the biggest layer of the DNN. Instead, we can choose a reasonable big memory to store most of the layers. And each layer bigger than the memory can be broken down into several kernels. For example, if a kernel requires 2 megabytes to store the weights, we can divide it into 2 kernels. The first kernel computes half the neuron, and the second kernel the other half, reducing the memory requirements of each kernel to 1 megabyte, enough to fit in the model memory. This configuration results in a 12 square millimeter chip. We estimate that the peak power of this unit is around 1.8 watts, and the average power is around 1 watt. For illustration purposes, I include these plots that show the execution time of each of the kernels that compose the TDS ASR system. The left plot shows the convolutional layers of the acoustic model and the hypothesis expansion kernel, whereas the right plot shows the fully connected layers and the feature extraction kernel. In conclusion, we think that the security and privacy implications of processing delicate data in servers are unacceptable, and we also think that programmable accelerators are likely the most viable solution for on-edge accelerator, given the limitations of fixed function accelerators. In this work, we have proposed a low-power programmable accelerator to perform acoustic speech recognition, a technology that is quickly getting into the mainstream. In this accelerator, the ASR system is implemented as a sequence of kernels written with parallel code. Additionally, each kernel has an associated set of functions to perform pre-kernel checks and operations. This computation model let us easily implement a wide range of speech recognition systems and execute them meeting tight time constraints, while operating in low power. Particularly, we have estimated that this unit provides 2 times real-time performance on a low-power configuration for an ASR system that provides a state-of-the-art accuracy. Okay, so thank you everyone for your attention. If you want to know more details about our work, please check our paper or stay for the Q&A session. Thank you.
Thanks, Dennis. I want to just see if he's, yeah, I'm just allowing him to talk. Dennis, can you, are you able to say something?
Yes, can you hear
Okay.
me?
Yes, excellent. Okay. Okay, we are all set. So, are there any questions? Please feel free to raise your hand or post it in the chat. All right. Maybe I can just start. So, you spoke about these different kernel level splitting of the weights. So, with all these optimizations, what's the largest network size you guys can compute on chip?
Mm, well, one of the goals that we pursued when we were designing the system is to avoid setting a limit on the size of the model that we can execute, because we saw that that was an issue with previous designs, especially those that require the entire network to be stored on chip. So we try to avoid those. So I'd say the design doesn't have any specific limit on model size. So one of the limits maybe the is that I described briefly, which is if the one layer is too big to store the weights in internal memory because we are prefetching them, that that will be limit the execution of this layer. But we are solving that by breaking the layer down into several, let's say, sub layers. So I think that should
I
solve that
see.
issue.
Right, right. I mean, probably the only constraint you would have is if you have a like real-time constraint, and then the latency would probably dictate the size. But from a storage perspective, I understand you're pretty much unbounded. Is that correct?
Yeah, yeah, that's it.
Excellent. Got it. Okay. Are there any more questions? Just waiting. Um, can you do you guys have are there any do you can you do any quantization? Do you do low precision computations, or is it all fixed precision or just floating point operations that you carry out?
Yes, we assume the system to be quantized to 8 bits, which I believe is a standard for neural network inference.
Right, right. Okay, that's good. Any other questions? I'm still waiting. Okay, maybe one final question. So yeah, I did see a paper you had made a comparison to the work from MIT as well. So do you guys feel that like some adding, say, a front end voice activity detector would actually be beneficial, like the way they've done, or is that something that can be kind of automatically assumed within your operation as well?
Um,
So it's basically from a power optimization, you can gate the entire chip if there is no voice act. So basically they have a voice activity detector at the front end. So is that something you guys can have in yours as well? Is that is it kind implementable there, or is that or do you have some way of doing voice activity detection in addition to just ASR?
Okay. Yeah, in this case, we haven't considered voice activity detection, so we just assume that it is done externally. As I said in the presentation, there is like a main thread that is executed on CPU. We assume that some part of that main thread, or maybe some other driver, is doing the voice activity detection. But yeah, I think probably if that is included within the design of the accelerator, we can probably use that to further optimize the system, or to make the implementation of ASR systems easier. So to simplify the programming model, that's probably the case. But I'm not sure. I don't know much about voice activity detection.
Never mind. Okay, thanks. Yeah, that's good to know. Yeah, that's what I assumed as well. All right, that's great. Thank you so much, Dennis. Yeah, really interesting. And yeah, I agree that there is obviously on-chip computation does have several advantages from a security standpoint. So it fits well in the theme of this conferences, the workshop as well. Thank you very much.